Okay, so welcome back. Today we're going to do something that is very basic, which is taking the first integral of the 6 trigonometric functions. And of course, I'm not going to edit the video, and because I want to see how fast we can do. And of course, I'm not going to skip the steps either, and not going to do something that's too fancy, but we're going to use the results from the derivatives of the trigonometric functions to help us. So here we go. First one, we have the integral of sine of x dx, but in the derivative result, we have cosine of x is equal to negative sine of x. How do we fix it? Well, we're going to multiply by the square of -1. So we're going to put a negative inside as well as outside, so that now if we try to take the integral, we'll be able to get negative, which is from outside, the integral of negative sine of x dx by the derivative of cosine. This is what we're going to get. We will actually get cosine. And then don't forget, we have plus c for a constant term. So let's move on to the next one. This one is very easy because we know that the derivative of sine of x is equal to cosine of x. So we can just simply take the integral right away to get sine of x plus c. All right, next one. We have tangent. So do we have any derivative of a trig function that's equal to tangent using the basic 6 different trig functions? No. What should we do? Well, first, we can actually try to rewrite tangent as, by definition, sine of x over cosine of x dx. Then we're going to do a u sub here on the side, which we're going to let u be the denominator. And again, when we do that, we are going to use the derivative of natural log of x that's equal to 1 over x to help us. But if we do that, of course, as u sub, we need to take the derivative of this substitution to get du is equal to, and again, by definition, we have negative sine of x dx. But we only have positive sine of x on the numerator. What should we do? Again, we can just do the same thing as what we do in the first integral. We will put a negative sign here and negative sign here, so that if we now do a u sub, we will just have 1 over u. And if we take the integral of 1 over u, it will just give us ln of u. So we have the natural log of the absolute value of u. But what is u? Again, by the substitution, we have cosine of x. And don't forget, when we finish it, we need to put the constant term plus c. That's it. So for our next one, we're going to play the same game. First, we're going to rewrite cotangent as cosine of x over sine of x. And then, of course, there's a dx. Then if we do a u sub by letting u be the denominator, sine of x, du will just be cosine of x dx. So that now we actually end up with integral of du over u. And again, what is the integral of 1 over u? It's just a natural log of u. So our answer will just be the natural log of the absolute value of u, where u is the denominator here. And don't forget, we need to have the constant term plus c. All right. Finally, we're going to look at the secant case. So this is a little bit tricky because, again, if we look at the results of derivatives of the trigonometric functions that we have, none of them is going to give us simply secant x. So what should we do? Well, first we can use the definition of secant, which is 1 over cosine, to give us this result here. Then we're going to do something a little bit tricky, which is I'm going to multiply both top and bottom by cosine as well, so that we now have 2 copies of cosine on the bottom, and then we actually have cosine of x on top. Next, I'm going to rewrite this as cosine of x over, and we're going to use the Pythagorean theorem, the Pythagorean identity, which it says sine square of x plus cosine square of x is equal to 1. And of course, we're going to rearrange it so that we actually get 1 minus sine square of x. And don't forget there's a dx here. So what does that do? Well, now if we try to do a u sub here, by letting u not be the whole denominator, but we're going to let u be just a sine of x, then we'll actually get du is equal to cosine of x dx, which is the numerator that we have. So if we do that, this is going to give us du over 1 minus u squared. And again, we have 1 minus u squared on the denominator. We can factor it out and use the partial fraction decomposition, so that we actually get 1 minus u and 1 plus u on the denominator. And what should we put on top? Well, we can use the covering method, because if we try to do that, we actually will get 1/2 on top for each case. And we can actually check quickly by adding them together. So if we add 1 minus u and 1 plus u together, we'll actually get 2, and then half it, we'll get 1, which is same as a numerator. So as we take the integral of this, we get 1/2 of ln of 1 minus u, and then plus 1/2 of ln of 1 plus u. And of course, if we have logarithm, we can just put them together using the product rule, or you can call it addition rule, depends how you look at it. So that in this case, we will have, and be careful, here we have 1 minus u. If we take the integral, we also need to put a negative sign. So we actually will end up with 1 plus u on top and 1 minus u on bottom, because now we actually get the, instead of the product rule, we have the quotient rule. And don't forget, we have a plus c. So now we just need to substitute back to give us the result, 1/2 of ln of absolute value 1 plus sine of x over 1 minus sine of x plus c. And of course, we can try to simplify it by multiplying both top and bottom by 1 over sine of x to give us 1/2 of ln of 1 plus sine of x all over, here we have cosine square of x, and then plus c to give us the final result, which is ln of, now if we bring the coefficients 1/2 in, we're going to take the square root, and we are going to have the positive square root, so that we will have 1 plus sine of x all over cosine of x, which is the same as secant of x plus tangent of x plus c. All right, that's it. So the last one, we're going to do something that's very similar, but since we're running out of room, I'm going to rewrite it on top here. So for the last one, we're going to look at cosecant of x. So if we're going to do the same thing, we're going to first rewrite cosecant as 1 over sine by definition of cosecant, and then we're going to multiply both top and bottom by sine, so that we actually get sine of x over sine square of x dx. And we're going to rewrite the denominator as 1 minus cosine square of x by the Pythagorean identity. And then we're going to do a u sub. This time, we are going to get u be equal to cosine of x. Or you can just put it as negative cosine of x, so that when we take the integral of, take the derivative of it, we will actually get du is equal to negative of negative sine of x dx, and the double negative canceled out, so that we actually get sine of x. So now if we substitute back, we actually get the top part be our du. On the denominator, we still have 1 minus u squared. And again, we will actually use partial decomposition fraction. So, well, partial fraction decomposition, so that we will actually take the integral to get 1/2 of ln of, let's see, we still have 1 plus u, and then minus 1/2 ln of 1 minus u. And don't forget we still have a plus c here, because there is no more integral. Then, as we combine them back, we will actually get ln, 1/2 of ln of 1 plus u over 1 minus u again, and then plus the constant c. And now substitute back what u is. We say that u is negative cosine. So now we get 1 minus cosine of x over 1 plus cosine of x plus c. And again, now we can just multiply both top and bottom by 1 minus cosine of x, so that the top is just a square, the bottom by Pythagorean identity, we have sine square. And we can just bring the coefficients 1/2 in, meaning that we're going to take the square roots, positive square roots, so that now we only have 1 copy on top. And then on bottom, we just have 1 copy of sine. And of course, we can just simplify it at the end to get 1 over sine, which is not secant, but cosecant of x, minus cosine over sine, which gives us cotangent of x, plus c. That's it.